Hello and welcome to yet another video on covariance vector. As you have noticed in the earlier video, I have given a detailed explanation on what is a contravariant vector, how contravariant vector induces into coordinate transformation, what are the notations and indices, and how from backward to forward and forward to backward we can do the transformation. This particular video deals with covariance vector. Now, in order to know about covariance vector, I have divided this video into two parts because covariance is something which is related to statistics as well as related to vector or physics. So the first part of the video would be primarily considering the essential aspects of covariance and variance in terms of statistics. Once we understand the basics of covariance and vector in statistics, then we can go forward and find out how covariant vectors and other things regarding coordinate transformation is involved. So first of all, we need to understand in this word covariance vector, what is a variance? As you see here on your screen, I have given a basic definition of what is a variance. Variance in statistics is a measurement of the spread between numbers in a data set. That means how the numbers are being spread out. It means also the measurement of how for each number in the set is from mean. That means from the mean how the numbers are deviating or they're converging, etc. So this is a basic idea of what is a variance. In statistics, it is basically the measurement of the spread. Now here is a nice and decent formula through which we can calculate the variance in statistics. I'm not going to explain too much of details of this formula because we will just take a basic understanding, and it is given with a sigma notation from I to n, x sub I subtracted from x bar whole square divided by n, where xi is the ith data point where it is varying from 0, 1, 2 up to I. X bar is the x sub I. X bar is the mean of all data points. That means we are calculating the mean. And n is the number of data points, the number which is being concerned. Now also this particular formula which you are seeing on the screen, this can be modified because generally this is used in terms of calculation of population. So if we use the covariance, variance formula in order to calculate the covariance, we get this. So covariance of x and y, which are the two variables, is a summation of x sub I subtracted from x bar, y sub j subtracted from y bar, whole divided by n. And this can be actually written in this term. This is the earlier formula, which is this one, the squared one, which can be also written in this part. And for sample covariance, we can write it in this way. Covariance of x and y, sigma summation of x sub I minus x, y sub j minus y, whole divided by n minus 1. Right. So let us see what are the values that mean. Xi are the values of variable in the x variable. Y sub j it denotes the values in the y variable. X bar means the average that we are calculating the mean of the x. Y bar means the mean of the average of y variable, and n is the number of data points. Now we are going to use this particular formula. So just have a look into this formula, that is a sample covariance, and we will just give you a very simple example of how we can use this formula and how useful it is. Consider the fact that there is an individual, Mr. S, or somebody, Mr. X, you can take any name as you wish, who has two companies, F500, a virtual company, and another company which is T500. In T500 company, Mr. S wants to add the money. So before doing that, he wants to find, is there any direct relationship? Is there any correlation or any covariance between F500 and T500? For that, what I have done is that I have just given a very simple example. So here you see I have listed down the number of years from 2020 to 2016. So we have got 1, 2, 3, 4, 5. The F500 and T500, these are the two virtual companies. And don't worry about this. These are the sales, that is the earning. It can be in dollars, it can be in dirham, it can be in INR, doesn't matter. So 100, 200, 150, 300, 600. T500 company has got 50, 100, 110, 120, 170. So the basic target that we are targeting from this particular chart is that can we find, is there any covariance between these two parts, so that before investing or before going to any decision, Mr. S can take a understanding. So see, what I have done is that I have basically calculated a mean. First of all, the mean which we have seen in the previous formula, the mean of F500. So 300, 600, 1200, 150. So 1350 divided by number 1, 2, 3, 4, 5. So here we have got 270. This is the mean of F500. In the similar way, I have calculated the mean of T500, 50, 100, 110, 120, 170 divided by 5. It leads to 110. So these are the two means of F500 and T500. Now you see what I have done. I'm just going ahead with the formula which we have shown it earlier. If you want to just have a quick glance, here it is. This is the formula that we are following. Okay, so you see here what I have done is that I have noted down the years, and similarly the F500, the values, T500, and in below in 270 and 110, these are the basically the mean, the average mean that I have calculated from the above part. Now A is basically this mean, the total, this one minus this one. This one minus this one. So 270 minus 100, 170, 70, 120. This is minus 30. This is minus 330. This is the value of A. Now you see what I have done in value of B. So in B, what I have done is that 110 minus 50, 10, 0, minus 10 and minus 60. So A and B is basically the calculation of this minus this with the F500s, and this minus this with the T500, and A multiplied by B is just a summation, just a multiplication of these two values. So I will just show you these two, A and B. These have been multiplied and these are the values, and then I have taken a total summation of this entire thing. Now you see that how I calculate the covariance. So the covariance of F500 company and T500 company is given by this part divided by n minus 1, which was the previous formula, and I get the value as 7750. See, here I have just noted down covariance of X. Sigma, I have already done the summation. Xi minus X is the this one, this minus this is the XY. Yj minus Y is the T500 company, where I have listed down this minus this. And then I have drawn n minus 1 is the total number of values, 5, 1, 2, 3, 4, 5. So there are total 5 years, as you can see, from 2020, 1, 2, 3, 4, 5. So n minus 1 is 5 minus 1 equals to 4. Now what does it denote? It denotes that 7750 is a positive integer. It is a positive number. That means that Mr. S can decide that it indicates that the two values of F500 and T500 are going in the same direction. So these two values, F500 and T500, which has been taken as X and Y in this formula, are going in the same direction, and that is why it is shown as positive. So now you have seen a classic example of what is correlation is all about, and from this particular formula, that is the sample covariance, I have taken a fictitious case study and I have shown you that what if this is positive. Now what will happen if this is a negative? Maybe that person can take a different kind of decision. That means the two values variables are going in a different direction and so on. Now this is something which is related to the statistical covariance, but this particular covariance which is in the statistical part also has some relation with correlation. Now here on your screen you see what is a correlation. Correlation actually is a statistic that measures the degree to which two variables move in relation to each other. That means here there are two variables X and Y which are moving in two different directions. This is definition 1. So co means together, as you see on the screen, I have written co means together. Correlation is the value which increases together. That means both of the values are going in tandem together. So co with together and relation. And correlation is negative when one value decreases and the other value increases. That means in this case of a particular study, as you see, This is positive because it has got a positive number. If would have gone something like -7750 or -5, that what does it mean? That means correlation is negative. That means one value is decreasing and the other value is increasing. So this is basically what do we mean by correlation. So this is a particular case study, and here on your screen you can see correlation's definition. Now what I have done also is that I have given a nice figure, I have now given a nice drawing of correlation. Say for example, this is a kind of a, you can say a TikTok, TikTok watch. This has got +1, 0 and then -1, right? So +1 denotes positive correlation, 0 denotes no correlation, minus denotes perfect negative correlation. I'm not going much more details into correlation because it is a different subject altogether in statistics. So this is what basically a correlation is about. This is a nice little graph which will give you an idea. The three ways this is pointing: -1, 0, -0, positive and negative. So 1 is positive, 0 has no correlation, and -1 is the perfect negative correlation. Here you will see I have just drawn few graphs. Now let me show you just one by one. So you see these dotted lines, right? These dotted lines can denote anything. It can be the price of the fuel, the price of the stock market, anything. This shows that it has got a very strong positive correlation, this particular graph. This shows it is a weak positive correlation, although it is positive, but it is weak. Why? Because these graphs or the numbers are more or less distributed. The second figure, this one, shows that it is a weak negative correlation. Why it is negative? Because the graph is pointing in this direction, right? Considering to other which was positive, which was positive in this direction, this graph is positive in this direction. This graph is also negative, which is slanting down, but it is moderately negative. The difference between these two, moderately negative and negative, is that the distribution of the data here is much dispersed. This is much dense. You see this? Distribution of data here, it is moderately negative because this is much dense, and this is relatively dispersed. This is wide apart. Now another example is that it has got no correlation. You see, I cannot draw either graph. Where will I draw? All these are dispersed. That means it has got no correlation. Now you see from the above example that I have shown, 1 is positive, 0 is no, and -1 is negative. So here you will see all these examples. This one is the positive one. This one is the weak positive, strong positive. This one is the negative one, and this one is moderately negative. But this is very negative. This is positive but weak positive, not distributed. So wherever you see this graph, you will find out the direction. So this and this are positive direction. This one and this one is negative direction. But in between the negative also, which graph has got a denser kind of a distribution of data? This has got a denser data. So that is why it is moderately negative. This graph has got widely dispersed data. So it is weak negative. This is positive, but this has got denser and this is weak. Why? Because again it is dispersed. And this has got no relation. So I have got it no graph or no line under it. Now, I can also denote correlation in terms of the sale of cold drinks during the temperature during the summertime. So I've just drawn a fictitious figure in terms of centigrade: 20, 25, 30, 35, 40, 42. As the temperature is going up, right, the sale of cold drinks is increasing from 10 to 20, 20 to 30, 30 to 40, 40 to 50, 50 to 65. So this is the number of sale of cold drinks as per the temperature which rises. So as the temperature rises, the cold drinks sale increases. As the temperature is less, the cold drinks decreases. This is a typical example of a correlation, and I can tell it this would be obviously in this graph. Why? Because it is a strong positive correlation. As on when the graph and the heat increases, the cold drink sale also increases. This is a typical example. This is what a correlation formula looks like, although we are not going much details into understanding what is a formula, but this is just for your quick recap. This is R equals to sigma of x minus x bar, y minus y bar, same taken a square root of that. So just note what it is. R equals to correlation coefficient. X bar is the average observation in the term of variable X. Y bar is the average observation in terms of value of Y. Okay, so what we have seen till now is that what is correlation and covariance in terms of statistics. Just to recap with you, this is an example of a sample covariance. What we have done is that we have taken a case study, and I have shown you that the values of two companies, F500 and T500, in order to invest or get a direct correlation, we have calculated the mean of both two companies, and then we have charted out this one. This one is this minus this. B is the mean minus the values of T500 multiplied, gives you the multiplication, and then we calculated the covariance, and it shows that positive covariance means it is moving, both the variables are moving in the same direction. This one is another example which shows the distribution of data in terms of strong, weak, weak negative, and moderate negative. And also this part which shows there is no correlation. Just a simple example how with the rise of temperature the sale of cold drinks moves ahead. Now we have got the time where we would be looking forward for the relation in terms of vectors. Well, just to give you a quick recap, I have to show you this. This is the contravariant vector which we have done earlier, but I will have to recap with this so that you can get a quick understanding of what this contravariant vector is all about. Just to make a quick note, I have drawn two axes, x1 and x2. This is a vector, not typically the v, but I have changed it to a. So the basis vectors are e1 and e2. As you can see, these two lines, e1 and e2, which are also unit vectors. I've given a typical example that what happens to a, that means this vector, if e2, that is this one, becomes twice of the size. That means e2 becomes e sub 2 prime equals to 2 times e2. Well, really nothing really happens until and unless we see this graph. In this new system, what I have shown is that a, which is the vector which I have positive, which is in this direction, well, this would be in red. So just to rectify it, just quickly let me write it in red, because this is the vector which has been written in red. Right. So this one a, which is how we can write a. We can write a as this is a prime e1, which is this one, plus a2, which is the new one, times e2 prime, which is this one. This is the e2 prime, right? And because e2 prime equals to 2e2, the component corresponding to a2 would be half of a2. And we have shown enough amount of examples on this. So this is the typical example of contravariant vector. Basis is being doubled. Where, yes, here the basis is being doubled, right? Basis is doubled, but the component becomes half. So here you see. So contravariant components are specified as superscripts and opposite of basis vectors, which are specified with subscripts. I think we have already gone through this, but this is just a quick recap on the indices part, which we have seen in the earlier video. In this earlier video, have you seen that this is the usual way in which we are writing, and this is how it changes. So v super I, this is the contra part, and v tilde I, it becomes a contra, and the basis remains at the same, right? So this is a quick recap of the contravariant vector, because you see that when this vector is doubled, the corresponding component is half. Right, so this is why it is called contra. Contra means which is opposite, and we have seen enough examples, but this is just a kind of a quick recap. Now we will quickly move on to our next part, which is called a covariant vector. For the covariant vector, I have drawn a graph, and I have to explain you one by one the different components of that. Now you see, this is a covariant graph. Let me explain you. It stands the same as the contravariant graph. So if you want to see this, you can see this one. See, this is the contravariant graph. Okay, all the components remains the same except this one. This vector a has been renamed as b. Right? See here, this vector has been renamed as b. So the origin remains the same, 0, E1. This has got a new one, B1. Now what we are doing is that we are, the contravariant components represents the parallel projections, which I will show you in another graph, whereas covariant components project in the in perpendicular manner. So that is why if I draw a perpendicular, you see these two angles are 90 degrees, right? So now it is time that we can go ahead with covariant vectors. Now we have seen, just keep it in mind that we have already seen what is a covariance. That means both the x and the y are moving in the same direction in order to get a positive covariance. Okay, so here E1 and E2 are the two unit vectors which we have seen, this one E1 and E2. How we can write B? Well, B can be written like this. I can write B equals to B prime E1 plus B2 E2. So B prime is this one, right? And B2 is this one. And this is the new one, B prime. So we are specifying using, now what, just note here, what we are doing is that this B we are representing in terms of covariant components. So what we can do is that we can write B sub 1. Okay, B sub 1 equals to B dot E1. Now this is basically the dot product of covariant components on the x-axis. So this is x1 axis and x2 axis. So what we are doing is that we are representing B using the covariant components in the x1 direction. So in the x1 direction, this is the B. Now just note that these are all superscripts. Here I have written B sub 1 because it is a scalar product. It is a scalar one. So we are taking a dot product of this B dot E1. In the similar fashion, what we can do is that we can use B2, which I have also written is a scalar product, equals to B, which one, dot E2, which is the dot product of the covariant of the x2 axis. So you see B1, B2, these are all perpendicular projection because it has got a 90 degrees. This one represents x1 axis, this one represents x2 axis. So this one, you see this one is the dot product representing x1, this one is x2 axis. Now what I am doing is that I have done a calculation. I am substituting the value of B prime E1 plus B sub 2 E2, and what I have got is this one. So you see B's value is equal to this. So I can get B1 equals to B prime E1 E2, E1 E1, which is this one, plus B2, this one, E2 remains the same, and the multiplication happens with E1. So that is why I have shown here, see a dotted line is mentioned over here, so that you can understand. So what I am doing, just a note, that I am substituting the value of this with this equation, this. Okay, so what we get is B1 equals to this plus this. Now let us see how we can get the value of B2. Yeah, B2 is this one, so we get B prime. Again, we have got E1 multiplied by E2. So just a second, let me see. Yes. Yes, now it is clear. So this paper light. Right, so what we have got from B2, we are getting B prime E1 multiplied by E2 from this equation plus B2, and E2 remains the same, and this value is again substituted, so E2 multiplied by E2. So this is what we get from substituting the values. Now what we will do, okay, so what it happens if with contravariant we do the same. So with the contravariant vector, if you see what we have done earlier, let me show you, we have doubled the magnitude. Here it is, you see this one. So here you see this one, we have doubled, E2 becomes 2E2. So this has been done in the case of a contravariant case. So let us see what will happen if we double it. So what I can do is that I can write over here, say I write, okay, E2 sub, it would be E2 sub. I have to change my pen, so you have to excuse me for that. It would be equal to 2E2, and this would be this is the older basis, so it would be written in the lower script, right? What will happen in that case, B will become equals to B1 E1 plus B2 prime E2 prime. Right? So from here what we can do is that we can write the total value in terms of let me move the paper over, right. So what we can do is that we can write B1 prime equals to, I'm writing it like this, B E1, okay, and this would be also equal to B prime E1 dot E1 plus let us say what would be the value of B2, it would be B2 prime, and then within bracket we have to write the value of E2 prime dot E1. In similar way we can write B2 prime, so we write the value of B2 prime equals to V dot, this would be E2 prime equals to B prime E1 dot, it will take time because this is something with plus B2 prime E2 prime dot E2 prime. Okay, right. So now what we can do is that we can express this entire term in terms of B2 and E2. So what I can do is that I can write, I want to express it. So just to write over here, expressing in terms of E2 and V2. Okay, so what do we find? So what we write over here, so this would actually show you the final result. So B1 prime would be equal to B prime E1 E1, okay, and then this would be plus B2 whole divided by 2, because I will show you the real meaning, within brackets 2 e2 dot e1, this would be a else arrow, and this would be closed. Similarly with v2 prime, we can write this would be equal to v prime e1 dot 2e2. Just mind it if I forget these arrows, just means the vector, so it is quite obvious, plus v2 by 2 2e2 2e2. Right. Now you see what happens over here is that this 2 and this 2 gets cancelled out. In this b2 part also, this 2 and this 2 gets cancelled out. And this equation, if I solve it, this will be more or less equal to the same b1. Right? And this equation will take two 2's, this 2 and this 2, and it would be more or less equals to 2b2. Now hold on for a minute. What actually happened? What happened is that if you see in this particular part, when we have doubled the this magnitude of this vector, when it has doubled, what has happened is that, okay, let me show you in this way. This particular equation, and this particular equation, this value has also taken a double. So you see, this e2 has been doubled, it has been scaled up to 2e2, and this part has also been scaled. So e2 has been doubled, along with this the magnitude has been doubled, and the vector components has also been doubled. Just note what happened in case of a contravariant vector. You see here, when this one is double, this has become half, and that is why we call it as contravariant vector. Exactly in the opposite way, this covariant vector is happening. This has been doubled, right? And this has also been doubled. So what do we analyze? What do we get from here? So contravariant transfers in the same way as the basis vectors. So covariant components transfer in the same way as the basis vectors. Covariant components are also specified using subscripts, same as basis vectors, which are specified with the scripts. Right. So you see there, here we have mentioned the scripts as lower values rather than the upper values, because earlier what we have seen is that in case of a contravariant vector, the contra part goes up and the other parts stays down. If you remember the earlier indices part, which I have shown it to you, let me see. Yeah, it is here. So I'm just referring to this. So you see this one, it has got the basis vector at the below and the contra part is on the top. So same happens over here. Here also we have seen that the basis part remains below. So the entire idea of doing is that when this has been doubled, this has got the value of 2b. That means though these two cancels out, yes, this b2 has been doubled. That means it shows that it is a covariant. Covariant means that the amount of magnitude which changes also changes with the basis vector. So just to recap again, that covariant transfers in the same way as it does. But also what I would like to tell you, here on your computer screen I have put in 3 important points. 1, vectors with covariant components are called covectors. Yeah, that is very important. That is the basic purpose of the video. Covectors are functions, right? So covectors rather than normal vectors can be termed as functions. So I will draw another video in which I am going to show you how covectors behave in terms of function. Covectors are specified with dual vectors on the basis instead of conventional basis. Although I have used all those arrows over here just to make things very clear, but you may remember one thing, that covectors are generally not denoted like this. They are basically dual vectors. I will make another video. So 3 point, vectors with covariant components are covectors. Covectors are used more as functions. Covectors are specified with dual vectors. Coming to the final part of the video, I will just try to give you a very simple example of what a covariance matrix looks like. Right. So just bear with me. This is what a covariant matrix look like. Now see, what I have done is that I will just quickly complete it. Won't take much of a time. Covariance matrix, I have drawn two figures, right? Two variables, A and B, right? And what I have shown is that when A changes to 1, B changes to 1. When A is 3, B is 0. When A is negative and B is also negative. So if, taking this into consideration, now if I draw kind of a simple graph over here, right? And I will just mention this as 1, 2 and 3. Okay, right. So what I'm going to do is that I'm going to take the first case. Say for example 1, and that is 1. So my graph goes like this. I'm so sorry for this drawing. This would be this. Okay. So when it is 3, I have to take, B is 0. So I have to take 1, 2, 3. So I follow up to this 1, 2 and 3, right? And I have to mention this one is the B. This goes in this way and this is the A, right? And when it is negative, this is negative. So 1 is coming out this way. So 1 is pointing in this direction, another is pointing in this direction, right? This is what is a covariance matrix. So in order to find out whether there is any covariance or not, let us draw a kind of a simple matrix, right? And I will show you how it looks like. So we can draw something like this. Okay. And what I will do is that I will just quickly put over some values. So say for example, I can write it as covariance. First part would be AA, right? Okay, this is not clear. Okay, I will just use a better one. Yeah, this part is clear, right? So I will use a better one. So let me take a bigger matrix so that I can draw it. So for example, I use let me use those A and B, and I will just tell you, say for example, okay, I will use a different color. It becomes clearer for you. So this part would be covariance. So for example, I want to find out the covariance between the first would be AA, right? As usual. Okay, let me see, let me draw in this way. So this will be a 2 by 2 matrix. It will become clearer. So 1, 2, 3, 4. 4 zones have been distributed. Here I will get covariance of AB, right? Here I will get a covariance of BA. And here I will get a covariance of BB, right? Right. Okay. So these are the values and this is the 1. So this part I can draw it as A and this one is B. Just you have to keep a note what it is going to happen. So covariance, it's covariance of the self matrix, that is A and A. These two are self. So covariance of the self matrix is basically where we find the variance. So I can call this one as the variance. Right? Similarly, covariance of BB, I can call this as a variance. Right? So covariance between, so point number 1 is covariant between the self, that is the self variables is a variance. So what is the relationship between covariance of AB and BA? Right? You must be wondering. Actually, it is the same. Yes, it is something like, if you can tell what is the difference between AB and BA. Between two variables, there is no difference, right? So you can tell it is commutative, but please note, matrix multiplication in itself is non-commutative. So don't go by this false notion that it would be. Here I'm just giving you an example that if I write covariance between AB, it would be equal to covariance between B and A. So in general, there is no difference. right? There is no difference between the covariance of AB and BA. That means that covariance matrix is also symmetric, right? Covariance matrix is also symmetric. Say for example, if I draw a matrix something like this, 1 2 3. See, for example, I write here 1 2 3, and then I write 2 4 5, and then I write 3 5 8, right? If I make this matrix as X, for example, so if I transpose it, what is the rule we know for the transpose? That this is going to write like this. So what we would get? So we will get 1 2 3, right? Then we will get 2 4 5, and then we will get 3 5 and 8, right? So this would be the transpose of X, right? So in this way, if you flip this part, if you flip that, covariance will also become a matrix, right? So covariance, the three important parts. One is that the covariance between the self part is basically it is the same. It doesn't have any difference. Number two, the covariance between the two variables AA and BE actually calculates the variance. The relationship between covariance AB and covariance BA is the same, and covariance matrix is basically a symmetric matrix, which means if you transpose it, it will give you back to the original matrix. So that is all. Although I have a small thing left, we have time. It is already 40 minutes. It's getting quite long. So let me try if I can put it in this video, or shall I try it with another? What I need to do is that I need to find out those values of A and B. So let me quickly put around. So A, and if I see B, and if I write those values, which I have got 1 3 and -1, and I've got 1 0 and -1. Okay, and I need to find out the covariance of A and B. Say for example A and B, right? So what I can do is that I can find the estimated value of this is the formula. So estimated value AB, right? And this would be the negative subtracted by the estimated value of A, right, multiplied by the estimated value of B, right, values. So this is the general formula. So what is AB? Say for example the estimated value of A and B. So I can take this part. This would be how much? So this would be equals to 1 into 1, then 3 into 3 multiplied by 0. So let us put it over here. So I can put it as a nice matrix. 1 into 1 equals to 1, 3 into 0 equals to 0, and then I have got -1 multiplied by -1 equal to +1, right? So we have got 1 plus 1, 2. So, and it would be 2, and how many values we have got? 2 by 3. So here I can put the estimated value, the expected value. This would be expected value. It would be equal to 2 by 3. So in this part of a matrix where we have got these values, we have got the first one, which is 2 by 3, right? So the covariance, so what we have got, that the covariance of A and B equals to 2 by 3, right? So in this way we can always tell that the covariance between B and A will also be 2 by 3, right? This part is also true. Why? Because in the previous matrix we have seen that this one and this part and this part is actually the same, and that is why it is a it is a symmetric matrix. And in this way we can calculate further values of BB and others. So in this way we can go forward and put up the values. So covariance between A and A. So can we calculate the covariance between A and A? Let us see that quickly. Oh, I need to use a different pen. Right. So in this part we can find out the covariance values between AB we have got, BA we have got, now we are calculating AA. So for AA, what we will do, we will use the same expected value of AA, which would be A squared, and minus expected value of, again, AA would be A squared, right? Here we get the value of find the value. So it would be 1, 3 minus 1. It would be 11 by 3. Here it would be 11 by 3. Minus, it would be 1, 1, 1. So it would be how much? It would be minus 1. So this would give value to 8 by 3, right? So how this one is calculated, I hope you understand. So I'm not going to elaborate on this part. So 11 by 3 minus. So covariance, and then the covariance between B and B. So let us see the covariance between B and B. Covariance between B and B would be the same. So it would be the expected value of B. That means it would be B squared minus expected value of B squared. This would be 0 because this leads to 0. This one would come to 0, and this one would come to how much? So this would be 1, 0, minus 1, and this would be 1, 0, minus 1. So this one would lead to 2 by 3. So here the value comes to 2 by 3, right? So I've done just in a haste because the time is running up. So what we can do is that we can put it now in a nice matrix. So the exact value would be, first one, covariance of AA would be 8 by 3. Covariance between AB would be 2 by 3. This leads to this, so automatically it would be 2 by 3, and this one would be 2 by 3, which we have calculated from here. So that brings us to the end of the video. I think you have enjoyed it a lot. It is a long one, but it is important. So this is what our covariance matrix looks like. This is how it behaves. We have already seen from here that if we double the values and how it actually changes. So covariance actually means it varies with 1 and 1. We have also seen what contravariant vector is all about, and we have also seen the statistical part, that how we can find out the values of covariant and contravariant vectors using statistics, and how it is related to correlation. This is the one which we have seen, and this is a typical kind of a case example through which we have calculated the values. That brings to the end of the video. The next video I would be bringing, but I would have to take some time because next few weeks I will be a little bit busy. So possibly next week we will be coming up with another video, and this time it would be probably on differential equations, or else I would take this part forward with covariant vector, and I would make another video which would be on linear mapping, and then we can proceed with the metric tensors. Thank you very much for watching. It has been a wonderful way, and it's really a wonderful joy that I get in making those videos. Please do subscribe, please do like, and if you have any question, please put up in the comment box. Thank you very much and stay well. Bye.